The rate of a chemical reaction can be expressed with a rate equation. The rate equation is a function of the concentrations of the reactants, sometimes the concentrations of products, sometimes the concentration of catalysts, and sometimes it can be quite complex, but often it's very simple. Often, rate equations will be very simple, and they'll have a form like this, where you have a variety of reactants, sometimes products, and the expression is just a simple product of the concentrations raised to exponents times a constant. So K is called the rate constant. And A and B might be reactants that we are having and some reaction. It could indeed sometimes see products in there as well. Okay, so there's some vocabulary we have to learn if we're going to be able to discuss these. So first of all, we call alpha is going to be the order of the reaction in A. Okay, so in other words, if I double the concentration of A, what happens to the rate depends on what this exponent is, whether it's a 1 or a 2. Usually it's an integer, but it doesn't have to be. Beta is the order of the reaction in B, and we could have more variables in here, but in this case let's just have 2. And the sum of all those exponents is called the overall order. The overall order only exists if the rate expression really is this simple. If we have something more complicated than this, for instance, if we had a fraction and then we had maybe A plus B on the bottom, then there actually wouldn't be an overall order. So the overall order is only true if we have this simple type of expression where it's just a product of a bunch of terms like this. Okay, so we sum up the exponents to get the overall order. So that's the vocabulary we need. A natural question might arise is, can we look at this overall reaction and come up with the rate equation? Can we find out what alpha and beta are just by looking at the overall reaction? And the answer is most emphatically no. So I'll show you why that's not true on the next slide. So suppose we have a hydroxide ion reacting with methyl bromide in a substitution reaction to give methyl alcohol plus bromide ion. When we run this reaction, we find it has a pretty simple rate equation. K is equal to the concentration of hydroxide ion. So the rate is equal to K times the concentration of hydroxide ion times the concentration of methyl bromide. Okay, so you would be tempted on seeing this to say, oh, I can always do that. There's one of these here, so the exponent here is 1, and there's one of these here, so the exponent's here, and so you can get the rate law from the overall reaction. But that is not always true. So let me give you a very, very similar reaction, and we can see what its rate law is. So let's say we have hydroxide, and this time we're going to react it with T-butylbromide. And once again, it's a simple substitution. So we end up with T-butyl alcohol and bromide. So what's the rate equation? Experimentally, we find out that the rate is equal to the rate constant times the concentration of T-butyl bromide, and that's it. There's no dependence on the concentration of the hydroxide ion. And we would be misled if we tried to get this rate equation by just looking at the overall reaction. So there's two different ways of finding these rate equations since we can't get it from the overall reaction. The first is to do experiments. And that'll be the subject of the next few videos of how you can use experimental evidence to get the rate equation. The other way is if you, from some other work, know the mechanism of the reaction. And the mechanism is the step-by-step procedure by which we go from products to reactants. So for instance, in this first reaction, the electron pairs on this hydroxide come and they hit the carbon here, and in a single step that bond is formed and this bond is broken. In this reaction down here, this bond breaks to form a positively charged ion here, and then in a separate step the hydroxide attacks. So the difference between those two procedures is called the difference in the mechanism. And by using mechanisms, we can find rate equations. And that'll be the subject of a future screencast. So for now, all we need to know is that we can't get the rate equation just by looking at the reaction.